Hi, this is Sally's Book Talk. Tune in daily for the best global books, all curated just for you. Today's book is Parallel Universes. Since ancient times, humanity has faced two ultimate questions. Where do we come from? And where are we going? These were once philosophical and religious questions, but modern cosmology turned them into scientific inquiries in the 20th century. The term universe first appeared in Zhuangzi's writings, combining spatial and temporal dimensions. Traditionally, the universe meant all space and time. But 20th century science revolutionized our understanding. We now know the universe is finite in both time and space. More astonishingly, since the 1980s, scientists suggest our universe might not be unique. Parallel universes. This book explores major advances in theoretical physics and cosmology since the 20th century. The parallel universe theory, also called multiverse theory, proposes multiple coexisting universes beyond our universe, like countless others. The author is Michio Kaku, Japanese-American physicist at CUNY, renowned science communicator. He's hosted radio shows and appeared on programs like Good Morning America and Larry King Live. This 336,000-word book has three main sections. Part 1 discusses cosmic creation, expansion, Big Bang, and inflationary theory. Part 1 explores wormholes, higher dimensions, and string theory. Part 1 examines cosmic fate, Big Freeze, and escape possibilities. Now let's focus on the core questions. How did the universe begin? And what will be its ultimate fate? First, let's discuss cosmic origins. While many think the Big Bang started everything, mainstream cosmology actually points to cosmic inflation. To understand inflation, we need to answer four key questions. 1. What is cosmic inflation? 2. How did inflation occur? 3. What purpose does inflation serve? 4. Why does inflation lead to multiverses? Let's start with the first question. What is inflation? The term inflation originally refers to economic inflation we experience daily. Economic inflation means significant increase in money supply over time. Cosmic inflation describes the universe's exponential expansion shortly after creation. Exponential growth is common in daily life. For example, computer speeds have grown exponentially, but nothing compares to cosmic inflation. According to inflation theory, the universe expanded unimaginably within fractions of a second, by a factor of 1.6, followed by 42 zeros. Don't check your phone. This number exceeds anything in daily experience. Imagine 16,000 followed by 7 billion units. How big is that? A 12-story building expanding to galactic size instantly. Post-inflation. The universe expanded from subatomic to macroscopic scale, smaller than a billionth of a PM2. 5 particle. How big did it become? About baseball-sized. Sounds unbelievable, but true. Right. This is the calculated result from inflation theory. Only after this did the Big Bang create neutrinos and photons. These particles shaped the universe we know today. Now, to the second question, how did inflation occur? This requires understanding. False vacuum. Let's start with regular vacuum. Many think vacuum is empty space. This is incorrect. Modern science proves vacuum contains energy. Imagine rolling hills with peaks and valleys as analogy. If you place a ball on this mountain, where would it stay still? The answer is obvious. In valleys, by treating mountain elevation as spatial energy levels, valleys represent vacuum states where objects stabilize. Vacuum is a stable space-time region. Even vacuums have energy variations, like valleys with different elevations. The lowest energy vacuum corresponds to the deepest valley, the true vacuum. Higher energy vacuums are false vacuums, like elevated valleys. False vacuum simply means higher energy vacuum. In 1981, physicist Alan Guth discovered cosmic expansion driven by false vacuum energy, like dough expanding in oven heat to become bread. Crucially, this expansion must be exponential. The origin of cosmic inflation. Third question, what's inflation's purpose? Inflation solves three cosmological puzzles simultaneously. First is the magnetic monopole problem. You know magnets. All magnets have both north and south poles. Cut a magnet and new poles regenerate automatically. Could single-pole magnets exist? Theoretically, yes. These hypothetical particles are magnetic monopoles. Physics predicts abundant cosmic monopoles. Why none observed? This is the magnetic monopole problem. Inflation provides an elegant solution. Imagine finding petals in a bowl versus the Pacific Ocean. Could you retrieve petals from the entire Pacific? Obviously impossible. Inflation expanded a building to galactic size in under a second, diluting monopole density beyond detection. Second is the flatness problem. Our daily concept of flatness applies only to two dimensions, like flat tables. These curved balls, both 2D surfaces. Einstein's relativity shows mass warps space-time. 3D space can curve like 2D surfaces. With infinite curved states, these single flat state curvature should dominate probabilistically. Yet observations show flat universe. Why this improbable state? This is the flatness problem. Inflation provides elegant solution. Why is the universe flat? Inflation flattened any initial curvature through massive expansion, like determining a marble's roundness versus Earth-scale sphere. Could you detect curvature in Earth-sized glass sphere? We don't notice Earth's curvature in daily life. Larger spheres appear less curved. Same principle applies. Inflation's expansion erased primordial spatial curvature. Third is the horizon problem. Analogy students taking identical exams in same room. Identical answers suggest collaboration. But how? Now, separate groups on Earth and Proxima Centauri 4.3 light-years away. Guess the result. their answers still matched perfectly. This is cosmic mystery. Identical answers confirm information exchanged between them, but separated by 4.3 light years. Even light speed communication would take 4.3 years. How did they achieve faster than light communication? Extend this question to the cosmic scale. Observations show uniform matter distribution across vast cosmic scales, implying historical information exchange. But the universe's vastness exceeds light's travel capacity since creation. How was superluminal communication achieved? This constitutes the horizon problem. Inflation provides the solution. Recall inflation's power, transforming a building into galactic proportions instantly. The student groups originally shared a classroom before inflation rapidly expanded their separation to 4.3 light years. Their information exchange occurred before spatial expansion. Finally, why does inflation create multiverses? This requires understanding eternal inflation. In 1983, physicist Paul Steinhardt proposed eternal inflation. Once it started, inflation never stops. Most realistic inflation models lead to eternal inflation. Analogy creating inflation requires false vacuum high energy vacuum state. Imagine false vacuum as giant apple tree. Energy creates cosmic apples universes. Ripe apples fall, allowing new growth, similar to universe formation cycles. Similarly, expanding universes detach from false vacuum, enabling new cosmic births. Eternal inflation theory suggests our universe is one apple among countless others on the false vacuum tree. The origin of multiverse theory. You might wonder, how many universes could eternal inflation create? The answer requires scientific notation, an unimaginably large number. For perspective, 100 billion humans have existed. That's 10 to the power of 11. Our Milky Way spans 100,000 light years, 10 to the power of 21 meters. During inflation, the universe expanded by 10 to the power of 60 times. Now, prepare for truly astronomical numbers. Cosmologists estimate 10 to the power of 500 universes from eternal inflation. Our universe might be 1 in 10 to the power of 500 possibilities. Let's summarize cosmic origins. Current consensus. The universe began with inflation. Inflation was cosmic hyperexpansion, transforming a building to galactic scale in fractions of a second. This inflation originated from false vacuum's high energy state. Early universe's false vacuum energy acted like oven heat, driving expansion while solving 3 key cosmological puzzles. Later research revealed inflation might never stop eternal inflation. This implies a cosmic apple tree producing 10 to the power of 500 universes, multiverse theory's foundation. Now let's explore cosmic fate. Hickson's Death's End describes 3 cosmic endings: Big Crunch, Big Bounce, Big Freeze. But modern observations rule out first 2 scenarios. In other words, the universe's final fate is destined to be the Big Freeze. To understand the Big Freeze, we must answer 4 questions. What is it? Why will the universe descend into eternal darkness? How does the universe evolve toward this frozen state? Can intelligent life escape this cosmic doom? First question. What is the Big Freeze? Let's start with temperature. Something familiar in daily life. Physics recognizes absolute zero. 273, 15 degrees CZ, 0 Kelvin. Why is this the coldest possible temperature? At this temperature, atomic motion stops completely. Everything freezes. Obviously, life cannot exist at absolute zero.
The Big Freeze predicts universal, absolute zero, no stars, no life, only darkness.
Sounds terrifying, right?
A frozen, lifeless, cosmic graveyard. Unfortunately, observations confirm this as our universe's ultimate fate.
Second question. Why eternal darkness? Before freezing, the universe will first experience permanent darkness. How does this happen? Earth's vitality comes from continuous solar energy input. All energy sources, wind, water, fossil fuels, ultimately derive from the sun.
Without solar energy, Earth would become lifeless.
What powers the sun? Nuclear fusion at its core. Lighter nuclei combining into heavier ones, releasing energy. This process powers hydrogen bombs too, fusing hydrogen into helium. In the sun's core, extreme heat and pressure enable hydrogen fusion into helium, releasing enormous energy, the sun's power source. But the sun's nuclear fuel is finite. In 4-5 billion years, the sun will exhaust its hydrogen, fuse helium into carbon-oxygen, then face inevitable death. Eventually, the sun will expel its outer layers, leaving an Earth-sized core. All stars in the universe share this fatal destiny. Dying stars shed outer material while retaining their cores. 3 possible remnants. White dwarf, 1.44 solar masses. Neutron star, 1.443 solar masses. Or black hole, 3 solar masses. Currently, old stars die while new ones form. The universe still contains sufficient energy for star formation, but observations indicate eternal cosmic expansion. Star-forming energy will gradually deplete entirely. Eventually, no new stars will form in the cosmos. The universe will enter the degeneration era as stars exhaust their energy.
All stars will extinguish, plunging the universe into eternal darkness.
This darkness marks only the beginning of cosmic demise. Now addressing why the universe evolves toward Big Freeze. Let's start with fundamental astronomical concepts. Our solar system's planets orbit the Sun, which itself orbits the Milky Way's central supermassive black hole, with billions of stars. Every galaxy centers on a supermassive black hole, ranging from millions to tens of billions solar masses. Like the Milky Way, supermassive black holes are orbited by hundreds of billions of stellar objects, including smaller black holes. Now let's explore a mind-blowing concept. General relativity states moving objects emit gravitational waves carrying energy away, reducing kinetic energy. Solar system objects' gravitational waves are too weak for significant energy loss. Their orbital decay takes eons. Eventually, their reduced energy will fail to resist white dwarf sun's gravity, crashing into it. Similarly, galactic center orbiting objects will spiral into supermassive black holes via energy loss.
When all stellar objects are consumed, the universe enters black hole era, terrifying cosmic consumption.
But this isn't the end. Hawking's greatest contribution was Hawking radiation. Hawking radiation reveals black holes, emit thermal radiation. When cosmic temperature drops below a black hole's temperature, it radiates energy outward. Cosmic expansion will cool the universe toward absolute zero. Eventually, all black holes will radiate as universe cools below their temperatures. Energy loss causes black hole evaporation. Larger holes evaporate slower. Solar mass black holes evaporate in 10 to the power of 66 years. Andromeda mass, supermassive holes, take 10 to the power of 117 years. Given infinite time, all black holes will eventually evaporate completely. When all black holes vanish, the universe reaches its final state. That's the big freeze we previously discussed. By then, the universe will contain only drifting photons, electrons, and neutrinos. At absolute zero, these particles lose all energy, and motion ceases completely.
No celestial bodies, no life, no energy, only infinite darkness and cold.
This is our universe's ultimate fate. Fourth question: can intelligent life escape this fate? Important clarification. This refers to hypothetical supercivilizations harnessing galactic-scale energy, not current humanity. Could such godlike civilizations escape the Big Freeze? Michio Kaku proposed a sci-fi solution, escaping to another universe. This escape plan involves multiple steps. First, scan the cosmos for naturally occurring wormholes. Wormholes, Einstein-Rosen bridges, are hypothetical space-time tunnels connecting distant regions. Second, deploying probes to traverse and identify viable inter-universe wormholes. Third, create exotic matter with negative energy to stabilize wormholes against collapse. Finally, escape through stabilized wormholes to younger universes. Is Kaku's plan feasible? Frankly, the probability is vanishingly small. No empirical evidence exists for wormholes or multiverses. These remain theoretical constructs. Even if multiverses exist, eternal inflation suggests they'd be impossibly distant for connection.
Thus, even super civilizations likely can't escape cosmic freezing.
Parallel universes offer no guaranteed salvation from universal heat. Death. Let's summarize cosmic fate. Observations confirm the Big Freeze as our universe's inevitable endpoint. The Big Freeze predicts universal, absolute zero, complete thermodynamic equilibrium.
By then, the universe will be empty. No celestial bodies, no life or energy, only endless darkness and cold.
The cosmic freeze process has 4 stages. 1. Star-forming energy depletion initiates degeneration era. 2. All stars exhaust energy and die, plunging universe into eternal darkness. 3. Stellar objects lose energy via gravitational waves, falling into supermassive black holes. Black hole era.
4. All black holes evaporate via Hawking radiation, culminating in Big Freeze.
Michio Kaku hypothesizes galactic civilizations escaping through wormholes, though probability remained negligible. Modern cosmology, merely a century old, still faces countless cosmic mysteries awaiting exploration. That concludes our exploration of parallel universes. Find keynotes below until tomorrow.